Hello everyone. In this very last presentation of the JSAC2024, I'd like to talk about a backdoor that we named HiddenFace. And this is actually not for the first time that you will hear about HiddenFace, because in the presentation just before mine, Harasan from Train Macro already introduced you to HiddenFace under the name Noobdoor. But in this presentation, I will dive very deep into HiddenFace, and I will explain to you all the technical details of this backdoor. But first, please let me introduce you myself. I joined ESET in 2019, and I worked there as a malware researcher since then. My main research focus is on a China-aligned APT group, which we named MirrorFace. And MirrorFace is known for its exclusive use of the load-info backdoor. Besides MirrorFace, I also track the activity of the North Korea-aligned APT group called Kimsuki. So, enough about me, and let's see what we will talk about in this presentation. So first, I will introduce you to the MirrorFace APT group, and then I will move to the HiddenFace backdoor itself. I will explain to you how we discovered HiddenFace, how its execution chain works, and then I will expose you to all these technical details of the backdoor. So, first, the MirrorFace introduction. As I mentioned, MirrorFace is a China-aligned threat actor that has been active at least since 2019. Several companies, like security companies, attribute the activity of MirrorFace to APT10. But we are yet to observe a strong relation between those two groups, so we are currently tracking it as a separate group. As I already mentioned as well, MirrorFace is known for its exclusive use of load info in their operations. And lastly, MirrorFace exclusively targets Japanese entities. Well, this one is with question mark because, as you've heard in the previous presentation, Harasan mentioned that MirrorFace newly targets Taiwanese entities and Indian entities as well. But since we don't have the same observation yet, I'm still staying behind my statement. Regarding victimology, MirrorFace has been observed to target media, defense-related companies, think tanks, political entities, and academic institutes. And now, let's see, and let's have a look on the HiddenFace backdoor itself. So, HiddenFace is a backdoor in the form of a shellcode that was developed with a heavy focus on modularity. Besides modularity, it has some other interesting features, such as evasive techniques, communication in an active and a passive way, data categorization system, and utilization of domain generation algorithm, aka DGA. The overall complexity and versatility of HiddenFace surpasses load info in many ways. So this makes it the most powerful tool in the MirrorFace's arsenal we have seen so far. Following the common MirrorFace targeting, HiddenFace was observed being used only against entities based in Japan, in particular against political entities and academic institutes. We discovered HiddenFace during an analysis of an attack that was carried out in August 2023 on a Japanese research institute. In the attack, MirrorFace exploited a known vulnerability in the 40OS, or 40 proxy solution, and this was very interesting to us, because up until then, MirrorFace has been observed to use spear phishing in their attacks only. During the attack, load info was deployed on the compromised machine, so that was a clear indication to us that we are dealing with MirrorFace. And since HiddenFace was deployed shortly after load info, well, the attribution was quite straightforward. Not only HiddenFace itself is a very interesting piece of malware, but its execution chain is also worth mentioning, so I will start with this one. The execution chain is compounded of two steps: the HiddenFace installation and injection. Even though HiddenFace is injected into the process right after its installation, for the sake of simplicity, we split the whole process into the two mentioned parts. So everything starts with the schedule task that was created by MirrorFace on the compromised machine to ensure persistence. This schedule task launches Windows utility MSBuild with a specified XML file. The XML file contains a C# code which we named FaceX injector that is built and executed by the MSBuild. FaceX injector first reads the content from a hard-coded file path. And the following is the content of the file. So FaceX injector checks the validity of the IS encrypted payload by computing a SHA-256 hash out of the encrypted encrypted payload. And then it compares it with the first 32 bytes of the data. And if the check passes, the FaceX injector moves to the decryption of the payload. For that, FaceX injector computes a SHA-384 of the middle block from the red data, and the first 32 bytes serve as the IS key, and the remaining 16 bytes of the hash are the IS IV. Using the key and the IV, FaceX injector decrypts the payload, and the decrypted payload is an instance of HiddenFace. Once HiddenFace is decrypted, FaceX injector moves to the next step, which is IS encryption of HiddenFace using machine-specific information. To generate the machine-specific IS key and IV, FaceX injector first concatenates the machine ID value obtained from registry and machine's hostname. Then, again, it computes a SHA-384 hash out of the result, and as in the previous case, the first 32 bytes serve as the IS key, and the remaining 16 bytes are the IV. As the final step of the installation process, FaceX injector IS encrypts HiddenFace and stores it into the following registry. The 16 hexadecimal characters are taken from the machine's from the SHA-256 hash of the machine's hostname. And now let's see the second part, the injection process. The injection process starts very similarly to the installation process. Upon the scheduled task trigger, the FaceX injector is built and executed via MSBuild. Using the same machine-specific information, FaceX injector reads the payload from the registry, generates the IS key and IV, and decrypts HiddenFace. Then, FaceX injector executes a defined Windows utility, such as the perfmon.exe, and injects HiddenFace into the process of that utility. With this, HiddenFace is executed and begins its startup routine. One can see that this execution chain makes HiddenFace available in its decrypted form in memory only, which makes it very difficult to obtain in this decrypted form. Upon execution, HiddenFace first dynamically resolves all the Windows APIs that will be used throughout the whole run. Then it performs few evasive actions. First, it actually removes a part of the code that is responsible for the API resolution, and this ensures that any potential memory dump of HiddenFace will be actually malformed from this point. Then, it restricts DLL loading to Microsoft-signed libraries only, and it sleeps randomly in between 30 and 60 seconds. Both defenses are likely deployed to avoid being behaviorally analyzed by a sandbox or a security solution. And lastly, HiddenFace starts periodically checking all the running processes against a list of blacklisted applications. If any of these applications is found, HiddenFace terminates. Once HiddenFace is done with its defensive actions, it moves to start performing the malicious activity. In particular, it creates a mutex to ensure that only one instance is running at a time. It loads external modules, initializes internal framework, and starts network communications. The core feature of HiddenFace is its modular system. The modules are either built-in functions or shellcodes that are labeled by ID numbers. HiddenFace already contains several built-in modules that are immediately available for the operator to use. But besides those, HiddenFace also can load external modules from a file. And the operator can send additional modules to HiddenFace to extend its capabilities even further. On top of that, HiddenFace provides every module received from the CNC with an access to its internal framework. As I mentioned before, one of the actions that HiddenFace does on its startup is loading the external modules. We call the modules external because they are all stored in a file in an IS encrypted form. The file has a user-specific name and it's encrypted by a user-specific IS key and IV. Therefore, HiddenFace must algorithmically determine the file name, the IS key, the IV, based on a machine's host name and current username. This approach ensures that even if the external modules file is obtained, a forensic analyst still needs to know the particular machine information to be able to decrypt the file. Nevertheless, the decrypted file content is a set of external modules. And then each external module entry from the set contains following information. That is, module type, ID to identify the module, optionally additional label for the module. It also contains data that describes a specific time or a period which is used for scheduled execution. And finally, it contains either the module's shellcode or parameters for a built-in module. Then each module is executed based on its type. That means either immediately, at a specific minute every hour, every specified time every day, or every X minutes, or X minutes after the last check for running processes. The internal framework that is provided to every module received from the CNC enables the received module to access and modify external modules, to utilize internal memory storage, to list currently running modules, and also to make changes to the framework itself. One can see that this framework's functionality allows the operator to create a tailored environment with the needed capabilities for the modules received from the CNC server. Every framework's function is identified by ID, and the modules are using a lookup function to obtain and execute the desired function. By default, HiddenFace provides with the following functionality. So every received module can add or remove the framework's function, write, read, or remove data from the internal memory storage. It can also read external modules file, add module to external modules file, or write data to external modules file. In this case, if no data is provided, the file is deleted. And lastly, the modules can also ask to get a list of currently running modules. One of the ways that the HiddenFace obtains commands from the operator is through active network communication. We call the communication active because HiddenFace actively connects to a CNC server, establishes a session, and then periodically requests for commands throughout the session. HiddenFace contains a hard-coded list of CNC URLs, including templates. And these templates are used for domain generation algorithm to generate the CNC domains. Also, HiddenFace uses a custom protocol over TCP, particularly on port 443, which is usually used for HTTPS communication. As I just mentioned, HiddenFace uses the DGA algorithm to generate CNC domains out of hard-coded templates. On this slide, you can see two examples of the templates. The second one was already shown to you by Harasan, and I will use this example to explain some details. So, HiddenFace and its DGA algorithm uses and distinguishes three symbols. The first one, the $n, is a variable that will be eventually replaced with a generated string, such as the one that you can see on the example. In the examples, you can see that in mine is $n and in Harasan's is $j. This is because the character of this variable can be actually arbitrary. The second symbol represents a request to the algorithm to use the machine's host name to create a unique domain for that particular machine. And the last symbol indicates a request to increase the domain's lifespan to a defined number of days, because by default, the generated domain lasts only for 1 day. Once the domains are generated, HiddenFace attempts to contact a CNC server selected out of the whole list. All the messages exchanged between the HiddenFace and its CNC server are encrypted. The first few messages are RSA encrypted and are used to send collected information about the compromised machine and also to exchange the materials for key generation for the symmetric encryption cipher. Once the keys are generated, HiddenFace and its CNC server use the symmetric encryption cipher until the end of the established session. It's worth noting that HiddenFace randomly selects one of the following ciphers. The commands received from the CNC are handled by available modules. Therefore, upon a request for a command, the CNC server responds with the module ID and the necessary data for that module. HiddenFace executes a module labeled by that ID and passes the data to the module. The result produced by the module is sent back to the CNC server. In case the module ID is not found, HiddenFace considers the received data as an additional module. HiddenFace adds the module temporarily into the list of available modules, executes the module, and when the module finishes, HiddenFace removes the module from the list. Every module received, as I mentioned previously, is additionally provided with an access to the internal framework. Therefore, newly added modules can perform an arbitrary actions on the compromised machine or perform any actions provided by that framework. And the following are the built-in modules provided by HiddenFace. As you can see, the functionality of most of the modules is self-explanatory. However, there is one that stands out, and that's the one that reads the content from the file named msarray.tlb. This file is produced by a MirrorFace credential stealer, which we named msarray stealer. I will do a little detour from HiddenFace here because I'd like to describe you this malware. As to our knowledge, this malware was not previously described, at least publicly. MSRA Stealer is a very interesting passive credential stealer. Uncommonly, upon deployment, it's registered in Windows as a password filter and authentication package. Password filter is a Windows feature that is legitimately used to enforce password policies. But MSRA Stealer uses this feature to collect the credentials on a password change. And the authentication package is another Windows feature that is used to analyze logon data. But MSRA Stealer actually uses this feature to collect the credentials on users' logon. All the collected credentials are dumped into MSRA.tlb, and the content is AES encrypted. Since MSRA Stealer doesn't have the capability to exfiltrate the stolen credentials on the CNC server, HiddenFace is utilized to do the job. Besides the active communication with the CNC server, HiddenFace can also passively listen for the commands on the defined ports. Similar to the active communication, for the passive one, HiddenFace contains a hard-coded list of ports to listen on. But actually, before HiddenFace starts listening on those ports, it reconfigures Windows Firewall to allow the communication on those ports. The communication is encrypted, well, the same as in the active communication case. However, in the passive communication, every message is encrypted by AES-128 in the CBC mode. The AES key and IV are generated on the current hour in the specified format. The SHA-256 hash out of this hour serves as the AES key, and the SHA-1 hash serves as the IV. This approach enables HiddenFace and the operator to generate the same key and the IV without exchanging any secret. The commands handling in the passive communication works in a more conventional way than in the active communication. The received data contains a command ID and the command's parameters. The table shows the commands that are accepted by HiddenFace by default. Again, the commands are quite self-explanatory, but I'd like to mention that in the case of the execute shellcode command, before the shellcode is executed, HiddenFace actually turns this shellcode into module first. In this case, however, the module is not added to the list to the available modules and is not provided with the access to the internal framework. So far, anytime I mentioned any kind of data, we have abstracted it to a very simple form. However, HiddenFace actually uses a very complex system to structure the data, not only for communication, but also internally. Every structured data blob consists of header, metadata, and the actual data. The header has the format that you can see in the top table, and that is that it contains the total size of the whole data in bytes, the data section size in bytes, number of metadata entries, and maximum possible number of metadata entries. Then, every metadata entry has the format that you can see in the bottom table. That is, every entry contains the data size in bytes and the data type. The actual data consists of an arbitrary content, and the content heavily depends on data's purpose. Every data item is categorized, and the type is defined in the metadata. The sample that we fully analyzed actually distinguished more than 80 data types. To show you how the data are structured, we present a few examples. The first one depicts the categorized data of the exfiltrate file command received from the CNC server as part of the active communication. The second example depicts the categorized data that are internally passed between two functions to run a module. And that's it. So in conclusion, in this presentation, I presented you HiddenFace, which is a backdoor that was developed and exclusively used by MirrorFace. The backdoor is so far the most complex malware we have seen in the MirrorFace arsenal. As we have shown, HiddenFace was developed with a heavy focus on modularity. This enables MirrorFace to tailor HiddenFace to current needs. And not only the capabilities can be extended by modules, but also HiddenFace provides an internal framework that enables extending the capabilities of the modular system itself. And this pushes HiddenFace's modularity to another level. Besides modularity, HiddenFace utilizes other interesting techniques and mechanisms, such as DGA, data structuring approach, various anti-detection and analysis techniques, and also the fact that HiddenFace is executed via a protective chain shows that HiddenFace is a tool especially valuable to MirrorFace. And lastly, all this indicates that HiddenFace is a reasonably big project to which MirrorFace developers must have put a lot of effort. So that's all from my side. I thank you very much for your attention. And if you have any questions, don't hesitate to ask. Thank you very much.
Okay, thank you very much. We'd like to open the floor to question. Do you have any question? Would you please stand up and get closer to the microphone if you have any question, please.
The talk is based on solid analysis result. I really like it. So question, you mentioned HiddenFace Ames Academic Institute, right? So my question is, so what type of information do they want to collect? So if you know that, I would like to hear that.
From what we can, what we've observed and what I can say is that they were after some very interesting information, let's say documents in particular, right? So, yeah. Mm-hmm. So it's like everything regarding MirrorFace is espionage.
Mm-hmm. Okay. Thank you very much.
ありがとうございました。
Thank you very much. Do you have any other question? And now we're providing that the simultaneous interpretation service. You can make a question in Japanese language. Okay, please.
Interesting presentation. I looked at this code as well, and I wanted to ask two questions mostly. The first one is that first off, regarding HiddenFace, I understand that it's shellcode, so there's not any compile times or anything, any metadata. So is there anything within the code that led you to understand the time that this code was created, if any?
Well, not particularly any part of the code, but our telemetry actually indicated that HiddenFace was used in the attacks at least since 2020, but it's even possible that it was used in 2019. But this one I can confirm. 2020 I can confirm for sure.
Was that loaded by the load info?
Sorry?
Was that loaded because it was loaded by load info or some other within the telemetry?
No, it was basically we pivoted on the FaceX injector that showed us, basically gave us all the metadata needed to conclude that it was used also in 2020. like in the case that I mentioned, that the research institute, that was actually like the only case we've seen like hidden face and load info together, because otherwise, like every time we've seen any kind of attack, it was a separate stuff, like either load info or hidden face, never together. Only this particular case, it was together.
Okay, thanks. Did you see any sort of variants of hidden face? Just some small modifications, or did you just look at one specific?
We did look at few samples. There were not like any extra differences. The one that I can like mention is that this passive mode, we've seen it only in one particular sample. Every other sample we've analyzed didn't have like this passive mode, only active mode. And also, which I completely like omitted from the presentation, hidden face uses proxies to actually like divert the traffic. In the other samples, the proxy like implementation changed a bit, or there were like hard-coded Google DNS servers and stuff to use. So, yeah.
Okay, thanks. Thank you very much.
ありがとうございました。
Thank you very much. Do you have any other questions?
よろしいでしょうか。それではご講演を終了させていただきます。ありがとうございました。Thank you, Dominik.